Welcome back everyone to GFE0007 Data Analytics Made Easy for Beginners. And today we'll be talking about lecture number 6, which is on similarity, neighbors and clusters. Now let's talk about the concept of similarity. So as a fundamental premise, if two things are similar in some way, then they often share other characteristics that we have not discovered yet. And we can see this logic every day. For example, in medicine, the doctor may match a symptom of his patient to a known cases that he has dealt with before to find for a diagnosis. And in law, a lawyer might cite precedents because of the current case might be similar to the one that he has handled in the past. So in data science, similarity gives us a way to organize a massive space of data points. So if we can measure how two things are more alike, then we can automate how a computer reasons about new situations when it comes. Now let's look at how businesses use this for retrieval. And this is about finding similar entities directly, matching one by one. For example, IBM might look into its database to find companies that look just like their best existing customers, so they know where to focus their sales efforts. And the Hewlett-Packard can do this using technology. For example, if a server is acting up, and then they find similar server configurations in their records to see how the previous one were fixed, so they can fix this one using the similar configurations. And this would essentially turn a very large and messy database into a library where we can search for similar cases. So we see similarity is being used a lot in recommendation system. For example, like retailers can use your history to predict your taste. And then in Amazon, Amazon can tell you that customers who viewed one item will also view another item, and they will try to recommend a new item to you. Or the Netflix can say that because you have watched Billy Elliot, and then you might want to watch another movie that they want to recommend to you as well. So what they do here is that they are using the similarity of your browsing or your viewing history to match you with the product or the people that share your profile. So we need to understand how the computers see this similarity. So we can represent object as a feature vectors, where this feature vector is just a fixed length ordered collections of numeric value, which we call as attributes. Okay, so let's say I want to divide the students in my class according to your demographic attributes. So I can look at your attribute, for example, like your gender, your age, which country or which states you're coming from, and several other attributes. Okay, and then I can think of this geometrically, where each vector is a point in n-dimensional space. Okay, so in 2-dimensional, it only has like 2 features. So 3 features, it will end up with 3-dimensional space. If more than that, then it will become a higher dimensional space. So the rule of thumb here is quite simple. Points that are closer together in that space, it doesn't matter whether it's in 2-dimension, 3-dimension, or higher dimension, points that are closer together in that space will represent entities that are more similar to each other. So for example, if I put you closer to another person, and in a 5-dimensional space, for example, so it could mean that you share many features with this person, 5 features with this person. For example, you share the same gender, the same age, the same state or the country you come from, and other dimensions. So how do we measure the similarity or the distance between one point and another? For this one, we may have like several measures of distance. And the easiest one would be the Euclidean metric, which is using this formula. Okay, so this is the most commonly geometric measure, and it is based on the Pythagoras theorem. And the way that this Euclidean metric measure is like as the crow flies, which means that if you are somewhere here, okay, and your neighbor is somewhere here, so in order for me to measure your distance to your neighbor's distance is I just cross a straight line from you and your neighbor, and this is the formula that we can use to measure the distance. And the next one is the Manhattan distance, and this is also called as the taxicab distance. So the difference between this and the Euclidean is that in Euclidean, we imagine if two person is located in a hall with nothing in between them, where one person can walk to the other person in a straight line. But in a Manhattan distance, we cannot use a straight line. Instead, you imagine if, let's say, you are at one building and then your friend is at another building, and in order for you to get to him is that you need to walk down the road, and then maybe you go to the right, then you go left, and then you go straight, and then you have to make a few turns because you want to avoid from hitting the buildings, and then finally you will arrive at your friends. And then the next one is the jacket distance, which is it used for sets of characteristics, and this is useful when the presence of trait is important but the common absence is not. So sometimes you may want to use the jacket distance to see how individuals are similar or dissimilar to each other. And the next one is the cosine distance, and this is usually used in the text classifications. Okay, so all of these distances measures is just a measure of distances between one point to another, and it's just that the calculation will be different, and some distances are more useful in certain cases. And after we're talking about the distances, now let's talk about the measures or the model itself. So we start with the model under the nearest neighbor reasoning, which is the KNN. So this is the K nearest neighbor or the KNN algorithm. And we can call KNN as a lazy learner because during the training phase, it doesn't really learn a formula. It simply stored the data as the data points. So when it is time to make a prediction for a new data set, it scans the database for the K most similar or closest instances, and then it combines the value of those neighbors to make the prediction. So what happens is something like this. So if I'm able to generate or I'm able to create like 3 groups within this classroom based on several features, and then when the new student comes in, I can just assign this student into any of the groups that I already have in the class. So let's say, and then I look at the feature of this new student, and then I see that these new students are more similar to this one group. So I just assign this student into that group. So now let's see how the KNN works for classification using the majority vote. So if we set K equal to 3, and the 3 closest neighbors are positive, positive, and negative, and then the prediction would be positive. And we usually choose the odd number for K because we want to avoid from having a tie. So KNN can also be used for probability estimation. So instead of a hard yes and no, we may give a likelihood. So if 2 or 3 neighbors are positive, and then the estimated probability is 2 divided by 3, or approximately 0.67. And sometimes we use the Laplace correction, which is a smoothing technique to prevent us from being 100% certain based on a very small sample, like a single neighbor. So we can apply KNN to regression for value estimation. For example, if you want to predict a customer's income, you can look at the income of a similar customers. And to get the final answer, then you take the average of the median of the neighbors' values. Now, let's look at this question. Should all the neighbors count equally? So a neighbor that is only 1 unit of distance away from you is much more similar than the neighbor that is 100 units away. So if we use the weighted voting, we can scale each neighbor's contribution by the inverse of its distance. And this will cause the specific number we choose for K to be less critical, because far away neighbors will have a less influence. And now we touch on the issue of complexity and overfitting. So for example, if K equals 1, then the model can be very complex because it memorizes every point. And this can include the noise, which will lead the model to be overfitted. So K equals 1 means that in one group, there's one member. So let's say there is 100 individuals. So each of these individuals becomes a group of its own. But if K equals n, which is K equals to the number of points, then the model can be too simple because it predicts the average of the whole population for everyone, meaning that all 100 people will be included in the same group, and this will cause high bias. So what we want to find is the sweet spot, which is usually what we do is, for example, if the number of observations is 100, and then we want to test different number of K values using the process called the cross-validation. Now we have the issue of intelligibility. So the KNN, basically it offers the local justification. What does it mean by local justification is that it is easy to explain a single decision. For example, if we want to tell a customer whether they were denied a loan because they are similar to others who were also defaulted on a loan before. But the global justification is hard to do because you cannot just easily explain the system's overall logic because there's no formula or a decision tree. Like there's no formula like in the linear regressions where you have the weighted parameters where you can tell a certain customers you are denied because of because of your scores is like this, or a decision tree in which there's a if then rule in which you can show to the customers that because of your attributes is like this, then we come up with a decision as such. So in some industries like mortgages, the legal regulations requires the model to be more explainable than a simple similarity search. So now we talk about the curse of dimensionality. K and N use every feature to calculate distance. For example, if you are observing like 10 features, then it uses every 10 features to calculate the distances. So if you have like 100 features, but actually among the 100 features, only 2 that actually matters, then the 98 features is actually the noisy features, and it can overwhelm the calculation. So to fix this, we use feature selection or manually give more weight to the important dimensions. Let me give you an example. Let's say I want to predict whether a student will pass or fail in this subject. So what I observe from you is you can have like 100 different features. You can have your CGPA, and you can have your what else? Your the number of credits that you are taking this semester, and then I can have many other features. For example, the distance between your hostel, your college to the class, and then many other features. For example, like your family background, your demographic background, and you understand, right? So let's say only 2 of these features are actually matters, which is your CGPA and maybe your distance from the class to to your place of living. And all the 98 the 98 features becomes a noisy feature. If we include that, then KNN will use all this feature to compute the distance. So that is why we need to do the feature selection. Now we also talk about the computational efficiency. So KNN is quite fast to train, but it can be slow to use because to find neighbors in millions of rows can be computationally expensive. So it is not ideal for things that need split-second timing, like bidding for online ads in real time. And now we shift to unsupervised learning, okay, specifically clustering. So in unsupervised learning, we have a target like predicting churn. In supervised learning, we should have a target variable such as predicting whether a customer will churn or not, or predicting yes and no, or predicting a numerical value. But in unsupervised clustering, we have no targets. So we're just asking if the data points naturally form groups. And this is used to explore a customer base or to find a new market segment. Now let's look at the hierarchical clustering, and this starts with every single data point as its own tiny clusters. So we then iteratively merge the two most similar clusters until we have a hierarchy of groupings. So you can look at these dendrograms. So the x-axis shows individual points. Okay, so this is the brand of the car, and the y-axis shows the distance between each clusters. So we can see that, for example, the Cadillac here is more similar to Lincoln Continental, but it is very different from Datsun, for example, or Volvo. Okay, so for example here, the Toyota Corona is more equal to Porsche. I'm sorry, I'm not very good in reading the car's name, okay, but they can be very different from Maserati Bora. Okay, so how do we know whether we want to group them together or we want to separate them into different groups? Okay, now let's look at the vertical axis here. So if, let's say, we draw a line somewhere in 400, at 400 here, so at 400, if we draw the horizontal line, so it will cut through two lines, which is one is this one and the other one is this one. So basically there will be two groups if you choose a height of 400. Okay, that means the Maserati Bora will be similar to Pontiac Firebird. Okay, and the Valiant will be similar to Mazda RX-4 because they are within the same group. So now let's go down here. Let's say we cut through at 180. So here we have four groups. One group is Maserati Bora. The other group is a group of this from Chrysler Imperial to Pontiac Firebird. And then the third one will be from Hornet 4Drive to AMC Javelin. And then the fourth one start from Honda Civic to Merc 280C. Okay, so it depends on where you cut on the branches of the dendrograms, and then you will know how many clusters you have. So how do we measure the distance between the groups in clustering? So we use what we call as the single linkage, complete linkage, or the average linkage. So the single linkages look at the two closest points between the clusters. The complete linkages look at the two farthest points, and the average linkage takes the average distance between all possible pairs. And now we introduce the k-means clustering, and this method focuses on the clusters themselves and each represented by a centroid, which is a geometric center. So unlike the hierarchical clustering, in this k-means clustering, the user must specify the number of clusters in advance. So you have to decide whether how many clusters do you want. So this is an example of the k-means clustering. So this is a very easy example. From the before the k-means, you can already see that the data is clustered into 3 clusters. So you can say that, okay, probably we want to introduce k equal to 3. So naturally, all the clusters which are similar to each other will be grouped as one group, and it will be differentiated from the other groups. Yeah, and in this case, it is easier to see because you only have like 2 dimensions. One here and one vertical, and the other one is horizontal. So imagine if we have like many dimensions, then it becomes quite difficult to see. So in the k-means algorithm, it follows the it follows the 4 steps which is being explained here. So the first is we randomly initialize k cluster centers. So for example, imagine the graph on the left one. So let's say we introduce k is equal to 3. So we can choose any 3 points. Okay, we can choose 1, 2, 3 here, or 1 here, 2 here, and 3 here. So we choose 3 cluster centers. And after that, we compute, we assign each of the points, each of the neighboring points to the nearest center. And then third is we update the centroids by recalculating the new mean of all the points in that clusters. And then we repeat the steps until we end up with having 3 clusters and 3 centroids that is able to differentiate between the points which belong to one group or another. So this is a repetitive steps until there is no more changes. And then we can evaluate these clusters using what we call as distortion. The distortion is the sum of square of the distances between the points and their centroids. So a lower number usually means it is a better fit. And to choose the best k, we graph the distortion and look for the elbow, which is the points where adding more clusters doesn't significantly reduces the distortion anymore. Now let's look at the practical implementations and the case studies. First, we'll look at this whiskey analytics, and we can have 68 binary features like PT or fruity, which is clustered, which is a clustering which reveal the taste group that don't always match geographically. I think for this one, I will share with you the case study together with the results and the graphs that you can see it. So it will come in a separate files. Yeah. And together with this one, this is another case study, which is news story clustering. So this one is also something that I will share as a separate file. Okay. And yep. So as a conclusion, the similarity and the distances are the core building blocks of data science. And KNN provides a simple but a local predictive power. Clustering will allow for discovery and exploration, especially for unstructured data. And success depends on the feature engineering, choosing the right data representation and distance metrics for the business goal. Okay. That's all for today's lecture. Thank you.